Testing. Hello. Hi, this is Lawrence Orijuela, and this is the accompanying video for Lab 2 of my CSE4010 course, Contemporary Computer Architecture. So, in this lab, we're gonna start. I'm going to start talking about logic gates. So, uh, so the way that this ties into computer architecture is well, hopefully at this point you've already seen uh, the material for chapter 1. I mostly talked about so this is the PowerPoint for chapter 1 that I'm using in CSE in the year 2022. Although this PowerPoint might look different in future courses of 4010 that I might teach. But anyways, so the reason why this lab, an understanding of gates, ties into chapter 1, well, perhaps I should give you an introduction first. So, one of the most powerful features of a computer is the power to make logic and make decisions. In the scope of computer architecture, complex forms of logical implementation can be performed by the most basic form of electronic circuit called logic gates. Okay? In essence, there exist 7 basic logic gates. There's the AND gate, the OR gate, the NOT gate, the NAND gate, the XOR gate, the NOR gate, and the XNOR gate. I'll provide more context in the accompanying video, which is the video that you're actually watching right now, actually. An actual physical gate may be created if the appropriate materials, a silicon wafer, capacitors, leads, etc. are present. And this is actually one of the things that I taught you in the very first lecture. So the manufacture of a chip begins with silicon, a substance found in sand. Because silicon does not conduct electricity very well, it is called a semiconductor. With special chemical processes, it is possible to add materials to silicon that allow tiny areas to transform to one of 3 devices: a conductor of electricity, an insulator for electricity, or an area that can conduct or insulate under special conditions, like a switch. Okay. So, over the years, we've gotten better and better at compacting a very small amount of integrated circuits into a very small computer chip, right? So in this lab here, you're going to recreate those chips in the form of logic gates, okay? So you're going to be simulating the gates using Verilog, okay? Of the 7 gates, NAND and NOR are referred to as the universal gates. What does it mean to be a universal gate? This means that every gate can be created by a series of NAND and NOR gates. And you'll then just do by part A, making a NOR gate using only NAND gates, and part B, making a NAND gate using only NOR gates, okay? So if you recall from Lab 1, the reason why we use Verilog is because, remember, Verilog is not a programming language. It is a hardware description language. It allows us to simulate different circuits, right? So let's get down to it. Let's talk about logic gates here. So logic gates are the basic building blocks of any digital system. It is an electronic circuit having one or more than one input and only one output. The relationship between the input and the output is based on certain logic. Based on this, logic gates are named as AND, OR, NOT, etc. So let's take a look at the AND gate first, okay? A circuit that performs an AND operation is as shown. It has N inputs where N is greater than or equal to 2 and only has one output, okay? So according to this logic diagram, we take, this is a circuit. If you see a circuit that looks like this, or it's curved like this, we indicate that this is an AND gate. So this particular AND gate takes two inputs, one called A and one called B, and it has one output called Y. So how exactly do we want the AND gate to work? It's quite simple. So AND, we only want AND to be true if the two or more outputs are true, right? So if we were to write a truth table for the AND gates, we would put A in one column for the inputs, B in another column for the inputs, and then we would map each possibility as 0, 0, 0, 1, 1, 0, 1, 1. And then we have our output, which is AB, but honestly, this should be called Y because we're calling it Y in our logic diagram, right? So we only want Y to be true when A and B equal true, right? That's how AND works, right? So as we can see, Y results in true only if A and B are equal to true, right? It's false otherwise, right? So if you have A and B equals 0, the output is 0. If A is false but B is true, the output will still be false. If A is true and B is false, the output will still be false. So the only time that we'll see true is if A and B equal true, right? So that's how the AND gate works, right? After that, we have the OR gate, which is as shown here. An OR gate is a circuit which performs an OR operation, which is as shown. So this is the logic diagram for the OR gate here. It looks kind of similar to the AND gate, in which this part is curved here, but the back end of it is also curved. So if you see a circuit that has this configuration, this is called an OR gate. Okay, so an OR gate has n inputs where n is greater than or equal to 2, and it also has one output, right? So in this logic diagram here, the OR gate has two inputs, which you're going to call A and B, and one output, which we're also going to call Y, okay? Now, the process of OR is usually represented using the plus symbol here. But if we're going to go off of our logic diagram, this should actually be called Y, right? So the way that this gate works is that the output is only equal to true if one or more of the inputs is equal to true, right? That's how OR works. So let's consider this. If A is false but B is true, the output will be true. If A is true but B is false, the output will be true. If A and B are both true, then of course the output will be true. However, if A and B were both false, the output would be false. That's how OR works, okay? Then we have a NOT gate, which is also referred to as an inverter. So a NOT gate it only has one input and one output, okay? So the way that this circuit looks like in circuit diagrams is that it's a triangle here. You might see it sometimes with a triangle and a dot, like that. Whether it's one way or the other, it's the same thing. It's always going to be a NOT gate if it has this triangle, okay? So because the NOT gate has only one input and one output, our truth table is a little bit smaller, right? So the way that NOT works is that it's very simple. It just takes the value that it's accepting and changes it to its opposite, right? So the way that the NOT gate works is that if its input A is 0, its output is going to be 1. If the input is 1, the output's going to be 0, okay? So of the three gates that we listed so far, AND, OR, and NOT, these are like the basic gates. But then we have the other four gates too, right? So these are the main gates. Oh, excuse me. the main gates are and, or, and not. All the other gates that I'm about to mention here, these are just, the other ones are just derivations of the other gates in some way. And we're going to look at those next. So we also have the NAND gate, which is named as such because it is not and. We abbreviate not and to be NAND. It has n inputs, where n is greater than or equal to 2, and 1 outputs. So the logic diagram usually looks like this. So you can actually represent it in one of two ways. You could put an AND gate here, and then have it followed by an inverter, like this. Or you could represent it like this way too, where you have the AND gates, but then you have this circle here, which indicates that there's an inverter here too. That also indicates that it's a NAND gate, right? So how does a NAND gate work? Well, a NAND gate works by taking what's the result of the AND of the two inputs and then inverts it. So if you look back to the AND gate diagram, so its outputs gave us 0, 0, 0, 1. If we were to not these, this would result in 1, 1, 1, 0, right? And that's exactly what we see here. 1, 1, 1, 0. So the way that AND works is that it's not AND. So the only time that NAND would be false is if A and B were both true. So if A and B were both true, or if A and B were both true, the output would be false, okay? But if it were any other combination, like say if A is false and then B is false, then the output is true. A is false and B is true, then the output's true. If A is true and B is false, the output would be true still, okay? That's how NAND works. Then we also have the NOR gate, which is not or, right? So let's talk about how the NOR gate works. Like going off of the previous gates, it's probably very easy to visualize what a NOR gate would look like, right? So it can be represented one of two ways. You can represent it like by putting an OR gate here, followed by an inverter. Or you could represent it by putting an OR gate here, and then having a circle like this, indicating that it's being inverted, right? So whether it's this configuration or this configuration, you should recognize it as an OR gate. Now, let's consider the truth table if there's two inputs, right? So how does this look? In order to get the results of the NOR gate in the truth table, we just have to take our results from the OR gate and then invert it. So if our output for OR was 0, 1, 1, 1, if I were to NOT it, this would become 1, 0, 0, 0. And that's exactly what we see here, 1, 0, 0, 0. Okay? So the only way that the output can be true is if both the inputs were both false, right? So 0, 0 results in 1. But if it were any other combination, it would result in false, right? So if A was true, if A was false but B is true, this would result in the output being false. If A was true and B were false, that results in the output being false. If A and B were both true, that results in the output being false, of course. So I covered the NAND gate or the NOR gate so far, okay? We have two other gates to talk about, but before I proceed, I need to point out something very special here. The NAND gate is a universal gate. And so is the NOR gate. This is also a universal gate. Okay, we'll get into that in a minute. But let's cover the last two gates as well. So now we have the XOR gates. So the XOR gate is a very special type of gate. It can be used in a half adder, full adder, and full subtractor, which we're going to talk about in Lab 3, right? So the reason why it's called XOR is because it's an abbreviation of exclusive OR, okay? So exclusive OR simply means that it means we will return true if one of the two outputs is true or the other of the two outputs is true, but not if they're both true, okay? So let's remind ourselves what the truth table of the OR gate looks like. I'm going to go back a few slides. So the OR gate looks like this. It's 0, 1, 1, 1. Now, the way that exclusive OR works, we're only going to make one change. We don't want XOR to return true if both A and B were true because it's exclusive. We only want one of the two inputs to be true, right? So instead of being 0, 1, 1, 1, this is actually going to be 0, 1, 1, 0, which you see here, 0, 1, 1, 0. Okay, so all the truth table of the OR gate or the XOR gate, they're the same except for the bottom part of the truth table. So let's talk about the circuit for the XOR gate. It looks like this. It looks like an OR gate, but it has another line here, okay, to indicate that this is an exclusive OR, okay? And in order to represent XOR in a logic diagram, we usually have it represented like this, where we have a plus here, but we enclose it in a circle like that, okay? And now this is probably all stuff that you learned from digital logic, but that's okay here because, you know, digital logic and computer architecture do overlap in some fields. So, yeah, so anyways, the way that the XOR gate works is that if A is false but B is true, this results in true. If A is true and B is false, this results in true. The only way that the XOR gate can return false is if both the inputs were both false or both the inputs were true. Okay, that's XOR gate. Now we have the XNOR gate, which is the last gate on the list. The way that an XOR gate works is just it's an exclusive NOR gate. So, and the way that this looks is that it looks very similar to a NOR gate, where you have an OR gate with a curve in front of it, but you also have an inverter here, okay? So, if you want to represent XNOR using digital logic, it's usually done in the form like you have this negative sign here enclosed in a circle, okay? That's how you represent XNOR. So the way that this looks is that, well, it's going to be very similar to an XOR gates. The way that this works is that we take an XOR gate, but we invert it, right? So if an XOR gate looks like this, 0, 1, 1, 0, as you can see here, if we decided to not this would result in 1, 0, 0, 1, okay? Which is exactly what we see here. So, wrapping this up, the way the XNOR gate will return true if both A and B were the same, like if they were both zeros or both ones, but it will return false if they were a mix. So if we had A was false and B is true, or A is true and B is false, this would both return in zeros, okay? Alright, so now I'm going to start talking about, so now that we've covered each of the 7 gates, if I go back here, Now I'm going to start talking about the universal gates. Okay. So, a universal gate is a gate which can implement any Boolean function without need to use any other gates. Okay. So as mentioned before, the NAND and NOR gates are called universal gates. So, so there's, if you recall from before, there's 7 gates total, and I demonstrated each one. There's the main gates, which are AND, OR, and NOR, but then, which I highlighted in yellow, and then we have the other 4 gates, which are different derivations of the 3. But then we have something called universal gates, which I'm going to highlight with blue, I guess. So we have the NAND gate, which is a universal gate. And we also have NOR, which is a universal gate. Okay, so when we say that it can implement any Boolean function without the need to use any other gate, that means that if you wire enough NAND gates, you can create any gate you want. Any of the other 6 gates you want. If you have a NOR gate, you can again create any of the other 6 gates that you want. So since NAND and NOR gates are universal gates, we can use this feature. In practice, this is advantageous since NAND and NOR are more economical and safer to fabricate than the basic gates. Okay, so in fact, one thing that you might not know is that an AND gate is typically implemented as a NAND gate followed by an inverter, and not the other way around. Likewise, the OR gate is typically implemented as a NOR gate and followed by an inverter. Okay, so if you wanted to see how exactly you can make every other gate using only NOR gates, here's the diagram that I would introduce you to. So, if you took a circuit, like the circuit for an OR gate or a NOR gate, you can create every other gate that you want. Okay, so if you wanted to make a NOR gate, all you have to do is take a single NOR gate like that. See. If you wanted to make an OR gate, this is how you would wire it. You would make 2 NOR gates. You would give these different names, maybe call it U1, U2, and you would take 2 outputs here, and you would feed the input twice into the inputs of the second OR gate. If you wanted to make an AND gate using NOR gates, you would configure it like this. You have 2 NOR gates here. You feed the same input of A into one of them, the same input B into one of them, and you take the outputs of those and feed it to another NOR gate, and then what you should find is that this results in an AND. Okay. Now I could go over the other ones here, but I think you guys get the point. If you wanted to see how all the logic gates can be created using NAND gates, this is the configuration. If you wanted to make an AND gate using only NAND gates, you would put one AND gate here. Maybe you give this a name, maybe U1 for unit 1. You put 2 inputs here, and you split the output as the 2 inputs for the next NAND gate, which we're going to call U2, and the resulting output should be the AND of A and B, right? And I could go into the other ones too, but there's no need. I'm just going to talk about what you need to do for the lab, okay? So this PowerPoint for the gates is going to be on Canvas. And now, let's go down to the material. So do you remember what I had you do in Lab 1? I'm going to I'm going to give you a reminder in case you forgot. So, let's do this. So, the purpose of Lab 1 was to get you familiar with creating gates using Verilog, okay? Do you remember we did this before? I had a circuit here, which I'm going to represent using a box, right? Most general circuits can be represented using boxes like this. Remember, in the very first, in Lab 1, for part A, I had you make a circuit that takes two inputs. Excuse me. It took one input called A, and it gave two outputs called B and C, right? You created a module for this, and you tested that using a test bench in Verilog. Remember that? In part B of Lab 1, you were tasked with making another circuit that has two inputs, X and Y. WX. And it gives two outputs called Y and Z, right? So the purpose of Lab 1 was to get you familiar making logic diagrams in Verilog, but here we're going to go a little more advanced and try something that's practical, which is implementing the gates, okay? So, going back to the lab. Yeah, so of the 7 gates, NAND and NOR are referred to as universal gates. This means that every gate can be created as a series of NAND gates or NOR gates, and I already showed you the diagram, the PowerPoint showing how they would do it. You will demonstrate this is true in part A by making a NOR gate using only NAND gates, and in part B, making a NAND gate using only NOR gates, okay? So this lab should be actually relatively simple for you. Well, it's gonna take some intuition to find out how this is being implemented, but this should be fruitful for you, especially if you might use Verilog in maybe some of your other courses that you're gonna take. Okay, so let's get started here. So as always, I'm gonna do part A for you, and then part B you can do on your own, hopefully. Okay, so let's get down to it. So open Visual Studio Code, click open folder, and select the Lab2A folder that you created before. Okay, so let's go ahead and do that. Okay, so I opened Visual Studio Code, and as you can see, I actually still have my Lab1A folder open. In order to get rid of that, all I gotta do is click close folder, and after that I can open a new folder. Okay, open a new folder. I want to go to the location where I saved my Lab1B folder. It would be right here. So before you had the Lab1A, now you're gonna open your Lab2A folder, which if you're just starting this lab, this folder should be empty, right? As you can see, that I have nothing in this folder currently. So here's what we're gonna do. Create the modules NAND gate and NOR using NAND. Okay, so you will create two modules in one .v file. Hover your cursor over the Lab2A folder in the Explorer pane and click the New File button. Name the new file NOR using NAND.v. Okay, that's what I'll do here. New file. Oops, excuse me. New file NOR using. How did I spell it? Okay, NOR and NAND are capitalized. NOR using NAND.v. Okay. So here's how we're going to do it. The first thing we're going to do is make a very simple NAND gate. And the way that we're going to do that is we're actually just going to go off the PowerPoint, okay? So let me go back. So let's remind ourselves what NAND looks like. So as you can see, the way it works is that it will return true if either A or B are both false, but it's going to return false if A and B were both true, okay? So let's implement that here. So the way we're going to do this is, I wonder if it's okay if I could put this here and put this here. Is that okay? Can you guys see this? Yeah, it's probably okay. So I'm going to make one module called NAND gate. And it's going to take, the NAND gate is going to take 3 wires, as you can see. So the 3 wires are going to be, as shown, the 3 wires are going to be let me do this actually. The 3 wires are going to be, 2 of them are going to be inputs called A and B, and the third one's going to be an output, which we're going to call C, okay? So actually in my program I call it Q, but they're just variable names. You can name them anything you want. So so I'm going to put my inputs and outputs over here because modules are functions and we need to list the parameters that go in each one. So I'm going to say A, B, and Q. I'll put a semicolon here. So I have all my wires here. The way that I indicate that A and B are input wires is using the input keyword. So I'm going to say inputs A, B, and that should indicate that both A and B are inputs. And now I need to indicate that my my output, which is Q, is an output wire, and the way I do that is using the output keyword. Q, like that. So now I have my 2 inputs A and B, but now I need to assign Q the value of the NAND of A and B. So how exactly I'm going to do that? Well, it's actually quite simple. All I got to do is use the assign keyword. Say Q equals, what are the components that make NAND? Well, I would simply take A and B and AND it using the ampersand symbol, and then I would NOT it using the exclamation point symbol. So I'm going to say A and B, put that there. So this will return the AND. If I want to return the NAND, I would put an exclamation point here. Okay? Wow, I hope you guys can see this. I wonder if I can make this a little larger. Appearance. Zoom in. Yeah, I think you guys should be able to see that. So as always, all modules need to be ended with an end module. So end module, like that. Okay, so now let's take a second and think about what I've done here. I created a module that's going to act like my circuit, right? This is going to create my NAND gate, okay? So this creates this here. But I got to remind myself, what exactly am I trying to do with Lab2A? Well, if I remind myself, I'm trying to make a NOR gate using NAND gates. And the way I do that is that now that I've created my NAND gate here, I can create my NOR gate using the diagrams that are in the PowerPoint. So now, because I'm trying to make a NOR gate using NAND gates, I would have to use this diagram here, wouldn't I? Okay, so let's tell ourselves how this is going to work. Now, I know that I gave you the code here, but as always, when you're doing your labs, you need to put comments in your code this demonstrating that you understand what's happening. So even though I give you the code here, you need to listen to this video to understand what the code's doing so that you can put the appropriate comments, okay? So, So I'm trying to make a circuit that represents this whole thing, okay? And inside of that underlying circuits, I have, inside of this circuit, I have 4 underlying circuits that are all NAND gates. So this is a NAND gate, 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 this is a NAND gate. So there's 4 NAND gates total that I need to use. Okay? Now I need to wire it in this configuration in order to achieve the functionality of a NOR gate, right? So this is how I'm going to do it. Let's make a new module called NOR using NAND. And it's going to take, as you can see here, it's going to have 3 wires, A and B, which are input wires, and then another output called, which we're going to call Q as the output wire. Okay. So I'm going to put A, B, and Q in here. Now I need to indicate to Verilog that A and B are inputs. So I'm going to do that using the input keyword. Input A, comma B. And I'm going to say output Q. Okay. Alright, so now you got to keep in mind that A and B and Q are not the only wires I'm going to have, okay? I'm going to have other intermediary wires. Looks like I'm going to have an intermediate wire here, here, and here. But we'll come to that later. Let's tidy this up a little bit. So you see this big square here? This is supposed to represent my NOR using NAND, okay? So now that I have that, I have to connect a bunch of these NAND gates into the configuration of this. So the way that I'm going to do that is, well, let's see. The first thing I have is, I'm going to focus on this NAND gate here first, okay? So I have a first NAND gate here, and I need to give it a name, okay? So maybe I'll call this U1, which stands for unit 1, okay? So I'm going to type this here. So I need to implement a NAND gate, one of my 4 NAND gates in total. But for the first one, I'm going to say NAND gate. This is the name of the module. I need to give it a name. So let's call it U1, like we do in the diagram. And I need to pass, and I need to pass 3 wires into it, okay? So one thing that I need you to understand is that when I declare a NAND gate like this, this is calling this module here. So so far, this module is calling 1 instance of the NAND gate. And as always, because of my definition here, I need to feed 3 wires into it. The first 2 are going to be inputs. The last one is going to be an output, okay? So if I was going off of my diagram here, let's think about what's being inputted here. So my very first NAND gate, which I'm calling unit 1, it takes 2 inputs, right? And both of those inputs are A, the wire A that I defined previously, okay? So over here in this U1, I'm going to say A, comma A, and those will be my 2 inputs. But as I can see here, there's also an output here that's going to feed into another NAND gate, okay? So I need to give this wire a name. I can't call it A or B because I already used those names already. So let's make an intermediate wire, and let's just call this C, okay? So the way that you indicate intermediary wires that are neither input wires nor output wires is just the keyword wire, as you can see here. And now I'm going to put C, which indicates that C is an intermediary wire, okay? So I'm going to put C here, okay? So that's the first NAND gate that I'm implementing into this module, okay? Now I want to implement, let's say I want to implement another NAND gate, okay? So Let's say that this NAND gate is called U2. So I make another instance of a NAND. Oops. I make another instance of a NAND gate. I'll call it U2. And as always, a NAND gate needs 3 wires, okay? That's because that's what I claimed it in the definition. It needs to take 2 input wires and have 1 output wire. Okay, so how am I going to wire this? So let's look at the diagram. So U2, which is this NAND gate here, it's going to take 1, 2 inputs, and they're both going to be B, okay? All right, so my input wire B is feeding into both inputs of U2, so I'm going to put B, comma B here. Now, the input wires are not the only thing I have. I also have an output wire, which is going to be an intermediary wire in the circuit. I need to give this intermediary wire a name. I can't call it A, B, or C because they're already used. So maybe I'll call this intermediary wire D, okay? Now, I need to tell Verilog that I have another intermediary wire. So the way I'm going to do that is that I could do it one of 2 ways. I could use the keyword wire again and put B, like that. But it would save a lot more space if I just kept it in the same line as the one that I already made. So here in line 15, I'm going to put a comma and put D in it, okay? So now I have 2 intermediary wires, okay? Since I'm calling this wire D, and this is the output of U2, I'm going to put another comma here and put D, okay? Now, you can easily imagine how I'm going to construct the other 2, right? I'm going to call this U3. So I'm going to do that here. So NAND gates, I'm going to call it U3. It takes 2 inputs, which are called C and D. So C and D. And it takes, and also has 1 output wire, okay? And this 1 output wire is going to feed into the 2 inputs of the very last NAND gate, which we're going to call U4, okay? This wire doesn't have a name yet, so let's give it one. I can't call it A, B, C, or D because they're all taken. So let's keep going down the line and call it E. So I'm going to put an E here, okay? And the third wire for U3 is going to be E, okay? Lastly, I have one more NAND gate called U4. So NAND gate called U4. And it's going to take 2 instances of the wire E as both of its inputs. So E, comma E. And then my output is going to be a new wire, which we're going to call F, okay? F, like that. So I have this good and wired. But I have one last thing to do. I need to assign Q to be the value of what my output wire is. So here's what I'm going to do. I'm going to, since F contains the value that I want Q to have, I'm just going to assign Q to be whatever the result of F is, okay? And now that we have that, I'm going to end the module. So this is very important when you do part B. Do you see how I made this module? I made this using the diagram from the PowerPoint, which I took nor using NAND, which I took from here, okay? So I made a wire, so I made a circuit that's just 4 NAND gates put into one, okay? And the way that I wired it is that I called 4 instances of the NAND gate and wired it correctly in the same way that I saw it in the diagram, okay? So what I should find here is that hopefully if I call a module of NOR using NAND, it's going to behave the same way that a NOR gate would work. Okay, so let's keep going down here. Let's see. Yeah, we did this already. Type the following code. The accompanying video provides an explanation of what the code is doing. The accompanying video is the video that you're watching right now. Okay. Code with no comments gets no credit, so make sure you put in comments. The way you put comments is da da da. Alright, so I'm pretty certain that this will work as a NOR gate as expected, but in order for us to see that it's really working, we have to create a test bench for it. Okay? So, how are we going to do that? So, here's what we're going to do. Let's create the test bench. Hover your cursor over the Lab2A folder and create a new file. And let's call it NOR using NAND _TB. Remember, _TB means that this is a test bench, okay? NOR using NAND _TB.B. Great. So, type the following code. The accompanying video provides an explanation. Enter comments explaining what the code does. Code with no comments gets no credit. Okay. So, let's go over each line one by one. So, first thing is the time scale. So, the time scale indicates the clock. I'm going to go 1 nanosecond over 1 nanosecond, and then I have to include my previous .v file, which is NOR using NAND.v. So I'm going to say include NOR using NOR using NAND.v. Okay. Okay, so now I'm going to create my test bench. If you recall, test benches are just modules, right? So I'm gonna use the module keyword, and I'm gonna call it NOR using NAND _TB. And the way that you indicate that this is a test bench is, well, the difference between a test bench and a normal module is that modules that indicate circuits have a parameters list. The fact that this one doesn't have a parameters list enclosed in open close parentheses indicates that this is a test bench, okay? Okay, so now that I have that, I want to test using 3 wires, because remember, this whole big box represents my module that I named NOR using NAND. How many inputs do I have? How many outputs? Well, as I can see, there's only 2 inputs. One I'm going to call A and B. A, B. And then there's 2 output that I'm going to call Q, okay? There's 1 output that I'm going to call Q, okay? So, when it comes to test benches, I have to indicate that something is an input using the reg keyword. So, reg A, reg B. And I indicate that something is an output in test bench using the wire keyword, wire Q. So that's it right there. Now I have to call an instance of NOR using NAND. Okay. So as always, in order to call that, I have to make sure I have my include, which I do. And now I have to call an instance of this using its name. NOR using NAND. Now that I have an instance of this, I need to give it a name. Okay. Now, I could name this instance of NOR using NAND anything I want, but I'm just going to call it UUT, which stands for unit under test. Okay. Now, as you can see from the .v file, NOR using NAND takes 3 parameters, 2 input and 1 output. So I'm going to pass these wires that I created as its input and output wires. So I'm going to say A, B, Q. Okay. Now I gotta indicate my other stuff too. So I need to set up my clock. The way I do that is using the keywords initial, begin, and end. So I'm gonna say initial, begin. Okay. Oh look, it automatically created the begin and end for me. Okay. So now I need these two lines of code here so that after the test runs, the outputs are being saved in the file that I can read later in GTK Wave. Okay, so I'm gonna say $, dump file, and inside of this function here, I need to give it the name that I want my VCD file to be named. So I want it to be named nor using NAND underscore TB.VCD. So nor using NAND underscore TB.VCD. Okay. I also need this function here, which is dump vars. So dump vars 0, nor using NAND underscore TB, like that. Okay. Okay. So now I can start doing my tests. Okay. So here's how this test is gonna go. At the very beginning of the clock, when the clock starts, initially A and B is going to be both equal to 0. After that, I'm going to wait 20 nanoseconds. And after that, I'm going to keep A at 0, and then I'll change B to 1. After that, I'll wait 20 more nanoseconds. Then I'll change A to 1 and B to 0. Okay? And then after that, after 20 more nanoseconds, I'm going to change A and B both to 1. Okay? So I'm going to say A equals 0, semicolon, B equals 0. Wait 20 nanoseconds, okay? A equals 0. Well, actually, I don't need to type all this. I can just copy this. Take that. Here, here, here. I will change this to a 1. I'll change this to a 1, and I'll change these two to 1s as well. Okay? Okay, so that should do it for my tests. Now, I'm not putting Q in here because I want to see what the result of Q is after it does these, okay? But after that, I'm going to have this line here. Now, the reason why we're putting this here, this display complete, is because it would be nice to have some kind of indicator in the terminal telling us that we've already completed our tests, okay? So I'm gonna put a $, display complete. So when it outputs complete, that means we know that our test is finished. Okay? So I think that's it for our code. As always, I'm going to leave it to you to put comments in here explaining what all of the lines are doing. Okay? But I think we're ready to give this a try. So here's what I'm gonna do. I'm gonna click save. Okay. I'm gonna press Control backtick to open the terminal. Okay. And now here's what I'm gonna do. I need to type in my command, which will create my VCD file. Okay. And that command is as such. I'm gonna put this here. Okay, maybe that's not gonna work. Maybe I should try. Oh, maybe I'll just type it out. Verilog -o nor using NAND underscore TB dot VBP, and then nor using NAND underscore TB dot V. Let's see if this makes our VCD file. Okay, looks like we have a syntax error on line 25. What did I do wrong? Line 25. Oh, I made a big mistake here. I forgot to put my end module. My bad. Okay, so now that that's there, I'm going to save it again. Save all. I can type the previous command again just by pressing the up key. Syntax error on line 12 of nor using nan.d. What could I do wrong? Line 12. What did I do wrong? Oh, I made another goof here. So there needs to be a semicolon here at the end of my line 10. So let's save everything again. Let me quickly type clear, which will clear my terminal. And then I'll press the up key twice so that I can have the same command again. Let's give it another run. It looks like it did it. I have my VVP file here, okay? So it looks like it did what it's supposed to do, but one thing that's supposed to indicate that it does what it's supposed to do is... oh, wait, no. The reason why it's not saying complete is because I didn't actually run the thing yet. Okay, so here's what I gotta do. Now that I have my VVP file, I need to run the next command, which is going to be VVP nor using band underscore tb.vvp. Let's see what we get. Okay, there we go. Now you see this in the terminal where it says complete? It's saying complete because we finished our tests, right? I told it to display complete after we finished our tests. And we know that it works because we see our VCD file here, okay? So now we can examine this using GTK wave. So GTK wave. Any second? Okay. So here is our GTK wave module. So before we actually look at the results, let's remind ourselves of what we want the results to look like, okay? We are trying to create a NOR gate using NAND gates, okay? The way we did that was we created a module called NOR using NAND, and it's implemented in a way that we took 4 NOR gates and configure it in a way so that that 2 inputs will represent a NAND gate, okay? So, a NOR gate. So, the way that this works is that hopefully we'll see a truth table that's visible, that looks exactly like the way a NOR gate looks like, where if A and B is both 0, the output Q will be 1, and then if there's anything else, it'll be 0, okay? So let's find out. File, open a new tab. I'm gonna open my VCD file. I'll open this. I'm going to select each of these 3 wires and I'll click append. Okay, so now that we have that here, let's see if it's working the same way that we want it to work. So remember, okay. Actually, I'm gonna use snipping tool for this. I'm gonna take this. Actually, let's take a whole thing. Okay. So we know we've succeeded if this behaves like a NOR gate, okay? So let's see. If A and B were both 0, and they are both 0 in the first 20 nanoseconds, we should see that the output is 1, okay? So since A is 0 and B is 0, we see that the Q is 1, so that checks out. In the next 20 nanoseconds, I changed B to 1, okay? So if A is 0 and B is 1, the output should be 0. A is 0, B is 1, and the output is 0. Okay, perfect. Next, if A is 1 and B is 0, the output should be 0. So right here, A is 1, B is 0, the output should be 0, so that checks out. Lastly, if A and B were both 1, the output should be 0. So A is 1, B is 1, and the output is 0. Okay, so perfect. It looks like it works. So recall what I did here. You're going to need to know these steps when you're doing part B, okay? And let's actually look at part B together. Let's see. If your Lab2A folder is still open, you can close it by selecting the folder and clicking File Close. Create a new folder in your CSE4010 labs directory and name it Lab2B. Open this new folder in VS Code. In part A, you've proven that a NAND gate is a universal gate by proving that you can create a NOR gate using only NAND gates. In B, you're going to do the inverse process. You will demonstrate that NOR is a universal gate by using a NAND gate using only NOR gates, okay? Now, I've already supplied the PowerPoint that you need to do this. So let's explore into how we're going to create a NAND gate using NOR gates. So it would be this diagram here, okay? So the way that you would do this is that you would name these, you would make a new module called NAND using NOR. You call this U1, U2, U3, U4, the same process we did for part A, okay? You would make a NAND gates so that showing that you would show that actually I think I need to show you something. Okay, so this is how you're going to do it. So you're going to make a Verilog file called NAND using nor.v. Okay, so I'm going to give you a tiny bit of a head start on part B for you. So let's close this folder, make a new folder, or excuse me, yeah, open a folder. New folder. I will call this Lab2B, Lab2B, like that. And then I will open this folder. Yes, I do. Okay, so create a Verilog file called NAND using nor.v, NAND using nor.v. In it, you're going to create a module called NOR gate. So in part A, we created a NAND gate. Here, we're going to make a NOR gate. So the way we're going to do that is saying module NOR gates. And if you recall from before, NOR is going to have 3 parameters: 2 input, 1 output. Okay. So let's remember what NOR looks like. Where is it? Yeah, here it is. So NOR is gonna look like this. We're gonna take 2 inputs A and B, and the output's gonna be called Q. A, B, Q. And then I indicate which ones are input by using the input keyword. A, B, output, Q, and then I assign Q to be equal to the NOR of to be equal to the NOR of A and B. Okay. All right, create a module called Lab2, and gives an input Q, which is the result of A nor B. So A nor B, that's just gonna be A is going to be A or B. Now, I believe you indicate OR in Verilog using the plus symbol, right? Let me just verify that, make sure that's true. I'm just going to open it in a new tab. Verilog, how to OR. All right, Verilog OR. How do you do OR in Verilog? I believe it's the plus symbol, but let me check to make sure. Yeah, it is the plus symbol. Although you could use the vertical bar symbol too. But okay, so it is the plus symbol. So this will represent OR. If I want to do NOR, I would invert it like that. And module. So here is your NOR gate. And now you will also create a module called NAND using NOR, using a series of OR gates to create a NAND gate. So basically, the process that I showed you for part A, you're going to do the same thing for part B here. And you're going to create your own test bench, simulate that works by testing every combination of A and B like we did in part A. As a result of your lab report, and then this will be it. And then for part 4, as part of your lab report, write the code for, but do not implement, how to create all 7 gates using NAND and all 7 gates using NOR. Okay? So I'm going to need this as part of your lab report. Just as good practice, showing me that you know how to wire a circuit in Verilog. I'm going to need you to show me how you're going to do the other gates too. Okay? So let me do this. So let's cross out the ones I've already shown you. I've already shown you how to do this, and I've already shown you how to do this. Okay? I already showed you how to do this, and you're going to do this on your own for part B. But I'm also going to need from you the Verilog code to show this as an OR gate using NOR gates. This one, this one, this one, this one, and this one. And I'm also going to need you to show this one, this one, this one, this one, this one, and this one, okay? So, a lot of things to do for this lab. And now, this might take a while, but it really shouldn't take too long because you already know how to do it. You just call this U1, pass A and B to it. Call this wire C, and then pass this into U2, right? Call this U1, U2, U3. And then pass these wires into it. These are going to be intermediary wires and then one output, just like that. So this is going to be good practice for you when you, for later labs. So after you do that, if you want, you could put this in you could put the code in just your lab report. But you don't have to make test benches for all of them because that would be a long time. So I just want the code for making the 7 gates using NAND and the 7 gates using NOR, okay? You can write this code using pen and paper and then take a picture of it and put in your report, or you can write the code in the same Word doc as your reports, okay? So here's what I need in the lab report. Use the lab report template found on Blackboard's Canvas. Your report must contain the following. I need you to write a brief paragraph saying what are the 7 logic gates, what are universal gates and why are they important. I want the written code to make all 7 gates using NAND, the written code on how to make all 7 gates using NOR, the source code for A and B, and then screenshots of A and B, okay? And if you deliver all those things to me, you will get full points, okay? So, yeah, this is the video for Lab 2. I hope you know how to do Part B now. I mean, you should. But if you need help doing this, I'm always available during office hours. And then, yeah, I think that's it. And now, I'll see you in the next lab video.